I'm Anthony Sala. In this video, we are continuing with our study of the ellipsoids, and in particular, we'll give some extra notes on the equivalence of the different ways of representing such an ellipsoid. You may consider the digression here as optional because somehow it's not needed to understand the basics of the other videos on this topic. But nevertheless, let's go. In a previous video, we said that we could express an ellipsoid in a direct, non-inverted form, x transposed px less than 1, or in an inverted form, x transposed q minus 1x less than 1. So if the ellipsoid is not degenerate and p is invertible, it's kind of equivalent. We also said that we may think of an ellipsoid as a transformation of a unit sphere via the matrix L when, if L is diagonal, we have an axis-aligned ellipsoid, and if L is not diagonal, then we have something else. We discussed the case in which a non-singular L allowed me writing this, so U transposed U could be written like this, and then this gave me the Q matrix I would need to express this ellipsoid in the quadratic form way. Of course, as Q was directly proportional to the square of the size of the ellipsoid, and L is directly proportional to the size of the ellipsoid, let's say, then informally Q is L squared, of course. Formally it's this thing, but okay, this requires invertible L. So what happens if L is non-invertible? Well, let's have a look. Let us first consider L to be, for instance, a couple of rows. So I map the 5D sphere onto a 2D ellipse. It smells kind of redundant, A 2D ellipse can be constructed by deforming a 2D sphere, but okay, let's see where these developments are leading us. So, in this case, we will consider the pseudo-inverse given by this expression. This pseudo-inverse verifies L dagger equal identity, so it's a right inverse of L, and in this case is the identity size 2. And this pseudo-inverse computes the minimum norm input U, which achieves a given x. What does it mean? Well, in here, if I fix x, I have 2 equations and 5 unknowns, so I have an infinite number of solutions, and the one with minimum norm, the least squares solution, is that with the pseudo-inverse, which we call here bar U. So, if x is the image of some point in the unit sphere, this means that this bar U must have norm less than 1, because otherwise, if this bar U had norm 2, then any other U giving rise to this x will have a larger norm. So I wouldn't find any U in the unit sphere fulfilling the equality. So x is the image of a point in the unit sphere if and only if this bar U has norm less than 1. So this is bar U, and this is bar U transposed, and miracle occurs because one L transposed simplifies by one of these inverses, so I get this expression, which is coincident to the one I got with the non-singular L. So if L is full row rank, linearly independent rows, then we can keep this expression. But in fact, as this thing is a 2x2 matrix, then for sure we would be able to find a 2x2 L that does the same job than this 2 times 5 matrix. But okay, I'll skip those details for brevity, but you may think on it if you wish. So now we'll consider the complementary case, having an L matrix which is full column rank, so L is kind of two columns, dimensions 5 times 2. So I'm mapping a two-dimensional circle to a 5-dimensional space. What would happen then? Well, it will result in a degenerate ellipsoid. What do I mean with degenerate? Well, okay, imagine that I have a circular lid of a frying pan in a table, so I consider it a circle in the plane in my table, but then I grab the lid and I just hold it in the air, so I transform it by a translation we are not considering, we are just considering the origin as the center and the rotation or whatever. Then okay, whatever I do, it will not increase the volume. My planar figure had 0 volume, and whatever linear transformation I do to it, it will still have 0 volume. So it will be, a degenerate ellipsoid, but nevertheless will be able to go on with the same formula, because as follows: imagine that I invent 3 more other rows, which will be Q, this will be L, and 3 more other dummy input variables, so that this will be 5D to 5D. And the columns of Q are linearly independent to the columns of L. For instance, with the null command or whatever, I can get those columns in one line in MATLAB. Details omitted for brevity. The thing is that I can complete the matrix until this is invertible. So good. Then, if this is invertible, it means that I can apply this formula with invertible L, now called M. And in fact, if the columns of Q are linearly independent to those in L, then this M epsilon will be non-singular for any epsilon different from 0. Then we have 5D to 5D mapping, invertible. So this 5D to 5D mapping of the unit 5D sphere tilde U will make this 5D x fulfill this equation, just changing L by M epsilon in here. But what is M epsilon transposed? Well, if I multiply L epsilon Q by is transposed, it will be L transposed epsilon Q transposed. So I will have LL transposed plus epsilon squared Q transposed, which is what I am writing here. So this is valid for any epsilon different from 0. Then, okay, the limit case with epsilon equal to 0 will make this disappear, and we'll have again the formula we are looking for, L transposed minus 1, identical to the full row rank case or the full rank invertible case. But in this case, it will be a degenerate ellipse, because this L5 times 2, L transposed, has rank 2. No new independent directions, no volume will be created. So this expression in here can be considered just as a, an algebraic expression and informal stuff, because the matrix is not invertible, so the actual inverse cannot be written. It's a degenerate ellipse, and this is kind of a notation as a shorthand for the limit case 0 volume degenerate ellipse. But okay, it's the same formula. So at the end, I transform the sphere, whatever the size of L or rank or whatever, will end up in the quadratic form representation as this thing. And in some cases, this LL transpose will not be full rank, so we need to be careful on that. But okay, as a quick way of remembering things, this is okay. So good. With this, we end with the transformation from the transformed sphere to quadratic form. And the last thing I wish to comment in this video is the case in which I have x transposed q minus 1x less than 1, then can I obtain the L that gives rise to the transformation of the unit sphere? Well, in fact, yes, we can, because in a previous video we already discussed that the transformation of the unit sphere via a diagonal scaling and the rotation rendered any arbitrary ellipsoid, and diagonalization recovered the rotation and the diagonal scaling. So, well, in order to have it written as one matrix times its transpose, it will be R square root of the diagonal stuff, square root of the diagonal, R transposed. So this will be L and this will be L transposed. So as this is important, let us just stress it in a new slide. Any positive definite matrix can be factored like this. And in fact, this factorization is not unique. But okay, if I can have this factorization, then this means that L is the matrix I was looking for. Good. And how do I obtain this factorization? Well, I just hinted the diagonalization way. If my matrix Q is VDV transposed, diagonal and V are the eigenvectors, then if I choose this thing as L, then V square root of the V transposed times L transposed, which is V square root of the V transposed again, because this is a symmetric matrix. So the thing is that V transpose V gives me the identity and this gives me Q. So the square root of the eigenvalues gives me a way to craft L, and in fact it's a very intuitive one, because the transformation L transforms the unit sphere by rotating to the axis directions via the eigenvalues and then scaling via the square root of the eigenvalues. So good, this is somehow a repetition of the diagonalization stuff we already discussed in other videos. And well, the thing is that there are other ways of finding this L transpose factorization. For instance, there is something called Choleski factorization, in which L is triangular and it's computationally more efficient in some contexts, whatever, but okay, we don't care. Maybe we do care that it's non-unique. Yeah, because if the unit sphere, I rotate it with whatever matrix I wish, rotation 1, then I still get the unit sphere, so there is 1 degree of freedom in the choice of this L up to rotations. So this factorization is not unique up to rotations. And well, we have some Choleski stuff, we have some diagonalization stuff, or whatever. The thing is that this is the way to go from matrix quadratic form to linear transformation of sphere. So we end with this. In this video, we highlighted some extra details on the equivalence on all 3 ways of representing an ellipsoid. 2 of them were via quadratic forms in non-inverted or inverted form, and the third was via linear expression changing the shape of a sphere. And with all the nitty-gritty details we have explained here, we have shown that the 3 of them are equivalent, except maybe some, degenerate cases in which some matrices might be non-invertible, and okay, so it's not so easy in degenerate cases, but okay, for the rest of us, we just can think on, okay, 3 representations are more or less equivalent. Thanks for watching.